Now we are asked to find the solution for this particular differential equation. This is basically a first order differential equation, which actually is a Bernoulli's kind. So we have to solve this by using that approach, okay? So if you remember in the class, we called the coefficient of y as p of x. So your p of x is 1 over x, and the coefficient of y squared is x ln x, so call that to be f of x, and the exponent for y is 2, as you see. So your n value is 2. So now your question at hand, dy over dx plus 1 over xy equals x ln x y squared is going to be like this. What I did here is I just divide the whole by y squared. So in dividing the whole by y squared, this is y to the power of minus 2 dy over dx plus, we see as you are dividing this by y squared, 1 over y is going to come, which actually is y to the power of minus 1. No more y squared, so x ln x can come. So now our intention is to change this to linear form, so call this to be v, y to the power of minus 1, you may call it v. So if you let v to be y to the power of minus 1, dv by dx is going to be minus y to the power of 2 dy by dx, which actually is minus 2. Okay, look, as you are bringing this minus 1 down, minus y can come, but as you are subtracting 1, minus y to the power of minus 2 can come. This, please correct this by minus 2, okay? Minus y to the power of minus 2 dy over dx can come. Anyway, this is going to be substituted by dv by dx. Then this is going to be dv by dx, as I told you earlier. This is dv by dx, and this will be negative 1 over x times v equals negative x ln x, because the one we are having here minus is multiple throughout. That's why I'm having here minus minus. So dv by dx is negative 1 over x times v is equal to minus x ln x. So this basically is a linear expression, so we can solve this linear expression by the formula we wrote before. So this is going to be obtained by integrative factor. The integrative factor is e to the power of the negative of p of x dx, but this is your p of x, your negative 1 over x. So take negative 1 over x here. In front we are having minus, so minus minus turns to plus, and this this will be, okay, e to the power of integral of p of a, the coefficient of, okay, the coefficient of v dx, the coefficient of v dx, and the coefficient of v is negative 1 over x. So e to the power of negative 1 over x dx is going to be what is that? E to the power of negative ln x. All right, e to the power of negative ln x, but that minus can be taken up, and e to the power of ln 1 over x, and e to the power of ln 1 over x basically is 1 over x. So the integrative factor is 1 over x. So having this means if you multiply this by 1 over x, you see everything changes to exact form, right? It will be an exact differential equation later. So let's multiply this by 1 over x and use grouping technique. So look, I just multiplied this expression by 1 over x. In doing so, 1 over x dv dx minus 1 over x square v, and no more x here when you multiply by 1 over x, and minus ln x can come. So now we can now consider this as, you see, a d by dx of v over x, students. If you carry out the derivative of v over x with respect to x, you will encounter this one, grouping technique, okay? I just grouped this one as v over x. Here I am having minus ln x, as you see. So, dear students, if you multiply both by dx and integrate, you will come across with this one. So v over x comes, and minus integral of ln x dx plus a certain constant follow, and from this v over x minus of integral of ln x dx. For this you need to use integration by part. Let you use u to be ln x and dv to be dx. So using integration by part, we can obtain this to be x ln x minus x. We do have negative outside plus a certain constant c. We knew what v is. What v is simply 1 over y. So this is going to be 1 over yx, right? And it will be 1 over yx minus x ln x plus c. Multiple this by negative. And finally, as you are solving this one, what comes here is just x reciprocal. And try to divide both by x, you will finally obtain the solution to be like this, okay? So y is 1 over x squared into 1 minus ln x plus xc. This is how you see this Bernoulli's differential equation is solved. And proceeding to the next question, question number 4, we have this one. It says use divergence theorem to evaluate this particular solution, this particular question. So how do you find now the solution for this by using divergence theorem? So for this, what we need to do is like as follows. So using divergence theorem, we do have this one. See, the surface integral is related with triple integral, as you see. So your function f here is a vector function taken to be this one, as you see. So we need to find the dot product of, this is the del operator with this vector function. This is very important. The nabla or the del operator dot with f must be obtained. But had you been solving this one by using this, would have been somehow complicated. Okay, so finding this is the same as finding this one, right? So we're now going to answer, you see, this one based on the triple integral. Okay, so we need to find the dot product between these two. So the dot product between these two is obtained by partial derivative with respect to x of the I component for x, partial derivative with respect to y of the y component, as you see, minus 2y squared, and partial derivative with respect to z of the z component, d squared. So the partial derivative of this is 4, and this one is minus 4y, and this is 2z. So this is already determined. Now it comes is, you see, integrating this triple integral over the given surface, so the given solid region D. The given solid region D is a sphere, as you see, a sphere of radius 3. So we need to use spherical coordinate approach. So this is 4. Your y is rho sine phi sine theta, and your z is rho cos phi. So the others are as they are, 4 minus 4 plus 2, all are written here. So your dv is rho square sine phi d rho d phi d theta. This is your dv in the spherical coordinate. So your rho runs from 0 to 3 because radius is 3, as you see, and your phi is from 0 to pi because it's a full sphere. And since again it's a full sphere, you see, we are going to take theta's range from 0 to 2 pi. So when we simplify this, you will encounter this integration 0 to 2 pi of 0 to pi of, now look here, this is rho square, so this rho square comes here, rho being rho cubed over 3, so 4 over 3 times rho cubed can come for this particular case. Just multiply these 3 terms by rho squared and then integrate that with respect to rho and evaluate from 3 to 0. Students, you will obtain this result to be 36 minus 81 sine squared phi sine theta, 81 over 2 cos phi sine phi, and then the phi and the theta can follow. Again here we can interchange these two guys because we don't have theta here. If we don't, I know, yeah, we can interchange basically because integrating the first one with respect to theta is simpler, and again this one is simpler, so we can exchange these two. So as you are exchanging these two, d phi and d theta as d theta and d phi, you need to exchange again these two, 0 to pi and 0 to 2 pi. So look, after exchanging we can have the integral 0 to 2 pi, but now here you see 2 pi minus 0 is 2 pi, 2 pi times 36, 72 pi. So this integral of sine theta is minus cos theta, minus makes plus. But you see what happens here is, as you are substituting pi cos pi is -1, and this one is cos 0, it will be 1 minus 1 minus 1 makes -2, so multiplying 2 by 81 it will be 162 sine squared phi plus. Here again, you see, after evaluation, you will obtain this to be 81 pi cos phi sine phi d phi, because we don't have here theta, so it will be 2 pi. You see, integral of 2 pi, integral of, what is that? Integral of integral of pi can come, and 2 is cancelled by 2. 2 pi can come, and 2 is cancelled by 2, and then we can have 81 pi cos phi sine phi d phi. Anyway, just try to find this integration and evaluate the integral from 0 to pi again. And as you see doing this, what comes here is the following one: 72 pi squared minus 162. So I can now undergo integration for each of these one by one. and you will finally obtain this to be as can be shown 72 pi squared minus 81 pi. Now after this, what comes next is, you see, question number 5, the last one, and it says use Stoke's theorem to evaluate this under a triangle ABC with vertices A, B, C as it has been given. So what we need to do is, the given vector is, you see, x plus yi plus 2x minus zj plus y plus zk. Okay, it's already available here. So what comes next is, look, we need to use Stoke's theorem. Stoke's theorem associates this one with line integral with surface integral, and we need to take the curl of f. The curl of f is the cross product of the del operator of the nabla operator with f, so have ijk plus minus plus, and this nabla operator or del operator is partial respect to f respect to z, and your components are of f are written x plus y to x minus zy plus z, directly obtained from this one, as you see. So in doing so, we can find this answer to be 2i plus k. So the curl of f is already obtained, so Stoke's theorem associates, okay, this line integral with surface integral. So the triangle is 3x plus 2y plus z minus 6 equals 0. Try to think of how you can find the equation of a plane provided that 3 points are lying on it. So you will finally come across with this expression. So your z is going to be your f of xy, the surface, just solve for z. You will have this expression. So your m is x plus y, the I component, the j component is n, and your, you see, k component y plus z is taken as it is as p. So the partial derivative of this respect to x is minus 3, the partial derivative of the plane with respect to y is minus 2. So using this Stoke's theorem that associates the line integral of a vector function with the surface integral of the curl of the function, we can obtain, as you see, this expression. We have read this in our classroom, students, if you remember, since we are having a positive orientation, because as you are moving from A to B and from B to C, you are moving in counterclockwise direction. You can just have these 3 vertices on 3 x, y, z axis and trace it. You will obtain, you see, the orientation to be upward. That's why I'm taking this. So everything is known now. M, fx, n, fy, p all are known. So this integration is done now with respect to, you see, the region R. So this is going to come. We knew what m and fx, n, fy, and p are directly taken from these expressions. So we can have this one. After simplification, one can obtain this to be 10x plus 6y minus 6. Okay, just simplify this expression. We'll finally come across with this. But now your dA is dy times dx. So, but in place of y, we can take, okay, we can take y to be this expression, as you see. And this is obtained basically making z 0, because you are on the xy plane. If z is 0 and solve for y, you will come across with this. And then you're having y range from 0 to this one. Your y range is from 0 to minus 3 over 2x plus 3, and dy dx can come, so everything is given in terms of x. So after simplifying this, you can obtain this expression, and a single integral with 1d is going to come. And after evaluating this expression, okay, after finding the integral of this and evaluating 2 and 0 one after the other, you finally come across with this result, 1663 over 287. So Stoke's theorem associates line integral with surface integral. Had you been solving, for instance, this for 3 sides of the triangle, it would have been very complicated, because you are expected to integrate 3 times for these 3 sides of the triangle. But instead of doing that, we better tackle by using this Stoke's theorem. We did simply this step and find the result.